Hi everyone, today we are going to look at the path sum problem from Leetcode. Given the root of a binary tree and an integer target sum, return all root to leaf paths where the sum of the node values in the path equals target sum. Each path should be returned as a list of the node values, not node references. A root to leaf path is a path starting from the root and ending at any leaf node. A leaf is a node with no children, like this: 7, 2, 13, 5, and 1. They don't have any children. Both the node at the left and the node at the right, they both are null. We don't have any nodes on the left or the right. So here's how it is. The input, it has the root of a binary tree where each node has an integer value, which is val, and the left and the right. Child pointers. And we have target sum, which is an integer representing the target sum for the paths. For example, 5 plus 4 plus 11 plus 2 is 22. So something like that. And so that is a path. A route to a leaf path. And and key definitions here are: a root to leaf path that starts at the root and ends at a leaf node which has no children, like 5, 4, 11, 2. It's a root leaf path, and 5, 8, 13 is also a root to leaf path. And a leaf node has left is equal to null and right is equal to null. Left and right, they both should be null. Like for 13, 5, 1, 7, 2, all these are leaf nodes. And the constraint here is the tree may be empty, that is root is equal to null, and node values and target sum can be positive or negative, and number of nodes is 0 to 5000. They can be anywhere from in the range of 0 to 5000. So here today we are going to write the code using the iterative depth first search approach with 3 stacks to simulate the recursive DFS process. So let's look at the code. Here's the code, and as you can see, we have 3 stacks here. The first stack is stores the nodes to process, and the paths no stack, it basically stores the current path, that is the list of node values for each node. And the sum stack, it stores the cumulative sum of node values along the current path. So instead of recursive calls, the stacks maintain the state node path sum for each branch. So this is how the algorithm goes. It first explores the tree by pushing nodes and then their corresponding path sums onto the stack, and pops a node, checks if it's a leaf with the correct sum, and adds valid paths to the result, and pushes the children right then left with updated paths and sums, mimicking DFS traversal. So let's look into the code. Here we have a tree node class. It defines a binary tree node with value val and left and right child pointers, and it's used to construct the tree from the input array. Okay, I'm thinking I'll just like write this algorithm here, just so that we can be very clear. So first it explores the tree by pushing nodes and their corresponding paths sums onto the stacks, and then next up it pops a node. Checks if it's a leaf with the correct sum that is equal to the target sum, and adds valid paths to the result. Third, it pushes children right then left with updated paths and sums making DFS traversal. Okay, let's go into the code right now. Here we have the pathSum method, and basically all it does is finds all root to leaf paths summing to target sum. We have the key components here and sort of results, and three stacks: stack, paths, and sums. Stacks for nodes, paths for the current path list, and sums for cumulative sums. So here's the initial push here. We start with the root node and its value as a path and its value as a sum. And we have this main while loop here. It processes nodes until the stack is empty. We have leaf check right here, and it adds paths to the answer if the node is a leaf and current sum is equal to the target sum. And we have child processing, pushes right and left children with updated paths and sums. And then we have a build tree method. Here it's basically constructs a binary tree from an array level ordered representation. It uses a queue for level ordered construction, starts with a root, processes nodes attaching left and right children from the array, handles null values to skip missing children. And main method, we have the main method that builds a tree and from the array calls pathSum and prints the result. So let's go through a example walkthrough. So we need to remember that the tree construction is level order construction here, that it assigns the children correctly and with null indicating missing children. And let's look into the pathSum method. So here we have the stack. So I'm using a whiteboard here, and let's do the stack here. So here in stack I'm pushing node 5 because that's the root node. Yeah, we have the stack, right? A stack, named stack, which has this nodes. And also before that, because we are dealing with stack here, I want to make sure I'm adding this yeah, because we are dealing with stacks here, I would just like to add this just a couple of words about this stack operations here. So here, let me just write stack operations. And so push, basically what it does is it adds an element to the top of the stack, and pop, it removes and returns the top element from the stack. Okay, this is very important because we'll be dealing with the stacks here, the three stack. So where is my other window? Here it is. So here so first we are pushing 5. Yeah, we are pushing the root node, so that would be 5. And for paths, again, like I'm just gonna copy this rectangle here. Why? Okay, I need the internet. Here the paths, and I'm gonna say that this is the stack, and this is going to be paths, and this is going to be sums. Yes, we are initializing everything with the root node, and here the root node is going to be in an array list, and it's and here it's going to be, yeah, just the current sum. As we can see here, yeah, it's an integer, and this is a tree node, and this is a list of integers, and we have done the initialization, and now the stack is not empty, so we are gonna pop. So what does pop do? It removes and returns the top element from the stack. So now we are gonna pop pop this, so 5 gets removed. And so what are we going to do with 5? It Yeah, it goes to node. So now the node is going to be 5. And the path is going to be 5. And current sum is going to be 5. So I'm just going to write it right here instead of, okay, I think I'll just do it there. And then so we popped everything, so the stacks are empty now. And these are the values here, and we are checking if the node dot left is equal to null and node dot right is equal to null. Yeah, obviously they are not null. We have values there. The node dot left is 4, the node dot right is 8, and so this is not a leaf node. And so the right child, first we are going with the right child, which is 8. We saw it right now, so we are pushing 8 to the stack. So let me bring the stack here. Hello stack. We are pushing 8 there. And then what's the next step? The next step is going to be new path. The path already has 5, and then we are adding 8 to it. So the new path is going to be 5 and 8. It's going to contain the elements 5 and 8. And paths dot push. Yeah, we're pushing into the paths. So what else we are pushing here? We are pushing 8 here, and for paths we are pushing 5 and 8. Okay, so here you go. So here we have 5 comma 8. And then what else? Sums. So sums, the current sum, like what's the current sum? It's 5, and 5 plus 8, what is that? It's 13. So, and then we are pushing it into sums. Okay, so here we are pushing 13 into sums. What? Oh no. Why? What's happening? What's happening? I don't know what happened. Something problem with my internet maybe. So I'm just gonna delete it and just, what is, oh, okay. There's something wrong with this. Okay, here we go. So let's say this is sums, and so what are we pushing into sums? We are pushing 13 into sums, and that's what we have. So the current state we have, I mean, yeah, we don't have to go there yet because we still have to do the left child. You still need to take care of the left child, and now the left node is not null. And what is the left node? The left node is 4. So, and here we are pushing 4 into stack. Okay, got it. So we are pushing 4, right? Yeah. So remember, when we push it, so what is it? Pushes the children. It adds an element to the top of the stack. Yes. And so here we have, oh no, there's something wrong with my Canva. Let me open my Canva again. Sorry about that. Looks like there's some problem with my internet. And okay, so here, oh no, everything's gone. So okay, I'm just going to create a new one now. Maybe I'm thinking I'll just go with, which template should I go with? Let me look at the templates. I'm going to go with, instead of whiteboard, the whiteboard seems to give me a lot of trouble. So I am going to go with maybe something that I'm, okay, maybe for business, let's look at some templates there. Docs, presentations. Maybe I'm going to go with presentations. Okay, here we have the elements, and so here I'm gonna say square or rectangle. So here we have the shapes there. Okay, got it. So now I'm going to make it smaller, and so let's just say this is stacks. Okay, I need a text box too. So first I'm gonna add the text boxes. We need 3 text boxes. this is stack, and this one it's gonna be paths. What? Where did it go? And this is gonna be sums. Okay, and just let me make it bigger. And here we have in stacks, we have 5. That's gonna be 5. And sum is 5. And then what else? What's gonna happen? So now we have, so this is the state we have. So let's go into the loop. This is the initial state we have after initialization. Yes. So that's what we pushed into it. And now we are going into the first iteration. We are popping everything, like node is pop stack, pop the stack and get the node, pop the paths and get the path, and pop the sums and get the current sum. So that would be the value we'd be getting. And so now all that's gonna be empty. And then here we are checking if it's a leaf. So the node we have is 5, and we know that it has both the right and the left child. We saw that just a few minutes ago. And at the right, do you remember what the right and the left is? It's obviously, yeah, the right is 4 and the left node is 8. Sorry, the left node is 4 and the right node is 8. And yeah, that's right. And so yeah, so we are like pushing now. So push 8 and push 8 to the new path, like we already got for the new path. Copy what we have in the path already and add 8 to it. And again, for paths, push the new path, and sums push 13. So these are going to be the new values that are going to be pushed in these stacks that stores these values. Okay, so the new values is going to be 8, and here we are, the new path is 5 comma 8, and here the sums is going to be 8. Actually it's no, we are gonna push 13 because, yeah, because its current sum is 5 already. So, and adding the node's right value and pushing it to the sums, so it's gonna have 13. And then left child is 4, so we are pushing 4 into it. So what does push do? It pushes, adds an element to the top of the stack. So 4, we are gonna say, we are gonna push 4 on the top. And then we are going to push 5 and 4. Okay, because as we can see, we're pushing 4, the path already has 5, and the node dot left dot val is 4, so the new path is going to have the elements 5 and 4. And we are pushing it to the paths. And so the sums, the current sum, we have 5, and we are going to add 4 to it, so it's going to be 9. And we are pushing it into the sums. Okay, got it. So now this is the state of the stack 4 comma 8, and paths is going to be, it's going to contain the list 5 4 that has 5 and 4, and the other list that has the elements 5 and 8. And the sums is going to contain the elements 9 and 13. And now we are going to check if the stack is empty. It is not, so we are gonna pop. Now we are gonna pop, what are we gonna pop right now at this time? So let's say, so what are we gonna pop? I'm gonna say iteration 2 here, so that we can have some space to write. So we are gonna pop the node. So let's say, like, it's gonna pop. No, I don't have to say iteration 2 here. I'm just going to write here. And so we are gonna pop, node is equal to pop. So what's gonna pop? 4. Yes, so we're deleting it, we are removing it, because pops obviously removes and returns the top element from the stack. So here it's going to be 4, and then path is equal to path dot pop 5 and 4, 5 comma 4. And current sum, it's 9. Okay, so I'm gonna take out the 9, remove and return, and I'm gonna check if the node dot left is equal to null, the node dot right is equal to null. The node is 4 right now. And let's check 4. Yeah, it has node dot left is 11, but node dot right is null. So because node dot left is not null, this is not a leaf, so it has so we are going to the next step, which is the right child. And it's checking if node dot right is obviously null, so we are not gonna go, we are gonna skip that. And node dot left, it's gonna push the node dot left, which is 11. And so let me just add it here. Okay, and then here the new path is gonna have the path, it's gonna have what's already there in the path, and then the node's left value, which is 9 11, so it's gonna have that now, and we are gonna push it into paths. So yeah, just copy and paste it here. So we are going to push that into paths, and 5 4 and 11, so that's what we are going to push now. 4 and 11, and sums dot push. Now what are we going to push here? What's the current sum? So the current sum is 9, and we are adding 11 to it, so 9 and 11 is 20, so we are pushing it to sums. Okay, so next, so this is the state of the stack at iteration 2 now. It's going to be like the stack is going to contain 11 nodes, 11 and 8, and the paths is going to contain the list with 5 4 and 11, and then other list with 5 and 8, and the sums is going to contain 20 and 13. And now we are in iteration 3. So what are we going to do right now is pop. So what are we going to pop right now? Node. What node we are in? Let's go to stack and pop the 11. Okay, and let me just save. So yeah, and path 5 4 and 11, 5 4 11. We are having less and less space here, so I'm just going to put it here. And the current sum, we are going to pop it from sums, which is 20. So now the current node is 11, so let's take a look at 11, and it has the left node, which is 7, and the right node with value 2, and so let's remember that. And now the right child, which is 2, right? Yes, the right child is 2, so we are going to push it to the node, push it to the stack. And the new path is going to have so what's in path? So this is what we have in path, 5 4 and 11. So yeah, we already have 5 4 and 11, and we are gonna add the right's value, which is 2, so 5 4 11 and 2. And then we are going to push that into the paths. So I'm just going to add your 5, 4, 11, and 2. And so the current sum is 20, and 20 plus 2 is 22. Yes. And now we have this left child, and what's the left child? Do you remember that? So the left child is 7. It is a node with the value 7, and it is, yeah, let me write it here, 7. And so the new path is already going to have the one that's already there, the 5, 4, 11, and okay, let me just copy and paste it here, which is already there. Yeah, path is obviously 5, 4, 11. So, and we are going to add 7 to it, because that's the current node's value, current left child's value. And now we are going to push it to paths 5, 4, 11, and 7. Let me add it here, or I can just so the, okay, let me just show it here. And so the current value, so the sums is going to have the current sum, which is 20. 20 plus 7, it's 27. And then, yeah, the stack is not empty, so we need to continue now. And where are we right now? So we are going to pop, just remove the top element. So 2, we are removing 2, and 2 is a leaf node. So let me just write it here. And path, we are removing the top element, remove and return the top element from paths. So it's going to be 5, 4, 11, and 7. Let me just copy it here and just remove it. And then the next one is going to be 27. So I'm just going to say 27. And yeah, we saw that it is a leaf node, so it's just going to add it to the, and if we had it is not a current sum, so it's not going to add it to the answer. And it doesn't have children, so these things are going to be skipped. And so let's check the state of the stack now. So here, let's just state now, like here the stack has 2 and 8 and paths, 2 and 8. Okay, I think I missed something there. Yes, because the stack is supposed to have 2 and 8. I somehow missed everything. I don't know how it happened. Yeah, I think I missed one iteration. I missed to update it for one iteration, I guess. So let me just so did we pop everything already? So now we are here and yeah, we did this one already. I'm sorry. So we did pop all that already, yes. Yes. Yeah, I'm sorry. So we did pop that and that's where we are right now. And now we are going to see if the next thing is like we are in the next iteration now, and what we are gonna pop, it's 2 5 4 11 7 and 22. Yeah, I missed this one here, 7 5 4 11 7 and 27, and then we have 2 5 4 11 2 and 22. So those are the things we popped right now. So just gonna put it in the next line here. So here I'm going to So current node is 2 here, and we are in iteration 5, and the current node is 2. It's a leaf node. So yes, and also the target sum is 22. So we are going to add it to the answer, which is 5, 4, 11, and 2. And it has no children, so it skips the pushes, and the next iteration it's going to pop again from the stack. What do we have in stack? So we have 8, 5, 8, 8, 5 and 8, and 13. So let's the current node is 8, so I'm going to check the node 8. It has both the left and the right children. It's the left is 13 and the right is 4, and so yeah, the left is 13, right? Yeah, and the right is 4. Yeah, so it's not a leaf node, and here we have this right is 4. So I'm going to push 4 there. Right child is 4, so I'm going to push 4 into the stack. And so the path already has, what does the path has? So the path has 5 and 8. So 5 and 8, and the current yeah, this one, it's 4. And the node's right value is 4, so we are going to add that to the path which we already have. So 5, 8, 4, we are going to push it to paths. It's going to be 5, 8, and 4. And then we have sums. So the current sum is 13, and we are going to add the node's right value, which is 4, and that's going to be 17. So I'm going to say, I'm going to put 17 here. And then we come to the left child, which is 13, and this is a leaf node. So here we are going to push the 13 there. And Actually, this is kind of confusing, so I'm just going to, okay, I think let that be there. So what I'm gonna do is here, so the path already has, what's the current path that we have? 5 and 8, right? Yeah. And the current left node's value is 13. So you're gonna push it to the 5, 8, 13. You're gonna push it to paths. And the current sum that we have is 13. And yeah, the current left node's value is 13, so it's going to be 26. I'm going to just add it there in the stack. And then now we are in iteration 7, and we are going to pop the node from the stack. So that's pop means return, remember, 13. So we're going to say 13, and return the top element, remove and return the top element 5, 8 and 13. And the current sum is sums.pop, which is 26. And it's leaf check. So the current node is 13. So let's check do the leaf check there. Yes, it is a leaf node. And so, but the current sum is 26. So we are skipping here, no children, so we are skipping there. And this is the current state we have. And so next iteration, it's gonna be, we are going to pop again, and now it's 4. Oh no, I think I'll just remove the numbers there. 4. And here the path is going to be 5, 8 and 4. And the current sum is going to be 17. So we're gonna, the current node is 4. Let's do the leaf check there. And yeah, it has both the left and the right node, 5 and 1. The right node is 1. And also it's like, so the right node is going to be 1 now. We're going to push that. So what's the right child for 4? Let me check that. The right child for the 4, it's okay. So the right child for 4 it's 1, and so I'm going to push that. Let me just write it there, 1, and so path the path it already has this one, and so I'm gonna add the current right node's value, which is 1, and so the current sum is 17 plus 1, which is going to be 18. The current sum is 1, and node's right value it's 1, and it's going to be 18. And the node's left child, we are going to push again, push on the top of the stack, so it's going to be 18, not 18 in a list, just the integer. So that is 5. We are going to push 5. Sure, the current path is 584, and add 5 to it. So the current sum is going to be 17, and 17 plus 5, it's 22. So now in the next iteration, we are popping the stacks, the node from the stack, which is 5, and the path is going to be, just going to copy that here. And the current sum is 22. And if the node dot left is equal to null and the node dot right is equal to null, let's check that the current node is 5, right? Yes, I think it's a leaf node. Yes, that's correct. It is a leaf node. And current sum is equal to target sum. Yes, that's correct. So we are adding the path to the answer. So this is the path. And then we are skipping it because it's a leaf node. And then now is the stack is empty? I don't think so. We have this, so pop it 1. And now we are adding popping the paths. Current sum, it's 18, I guess. Yes, it's 18. And now so the current node is 1. It is a leaf node. Yeah, it is a leaf node. Left and right, they both are null. And but the current sum is not equal to the target sum, so we cannot add to the answer. And because it's a leaf node, we have to skip it. And we are checking if the stack is empty. Yes, it's obviously empty. Yes, so finally we are done. It returns the answer. So the time and space complexity here is the time complexity is O of n, where n is the number of the nodes. And let me just save this one, and just, yeah, here, let me just take this one. So the time complexity is O of n, where n is the number of nodes. Each node is pushed and popped once. Path copying at leaves take O of h per valid path bounded by the number of leaves. And space complexity is O of h, where h is the height, tree height. Stacks store at most h nodes, paths and sums for a path from root to leaf. Each path in paths has up to 4 h elements, and so is not counted in auxiliary space. So for a square tree, the h should be n, so O of n, and for balanced tree, the h is equal to log n, so O of log n. So the key points in this code is it is an iterative DFS and it uses stacks to mimic recursive DFS, processing right child before left due to stacks LIFO, and path management. It creates a new array list for each child's path to avoid modifying the parent's path. and there's no explicit backtracking needed since each path is independent. It's right there. Let's create a new path for each child's path. And leaf check, we know the leaf check here, it's checking if the nodes right node is, the left node is null, if the right node is null, and it's checking for the currents, checking if the current sum is equal to the target sum, as it's given in the problem description, to make sure only valid paths are added. And we have stack synchronization. The three stacks, stack, paths, and sums are kept in sync with each pop and push, maintaining the node path sum relationship. And if we have to compare with the recursive solution, for the recursive DFS, it uses recursion stack, backtracking with a single current path list, and simpler code but less explicit state management, and spaces O of H for recursion, stack, and path. For this iterative DFS, it uses explicit stacks, no recursion, more complex due to managing multiple stacks, but the space is of H, same as previously for stacks, but creates new path list per node. So still O of H overall. And the trade-off here is recursive is more concise and easier to understand, but iterative avoids recursion, stack overflow for very deep trees, and may be preferred in some environments. So the edge cases that we have handled here is we are checking, we are base case, if root is null, it returns an empty answer list. And if there are no valid paths, if no paths sums to target sum, answer remains empty. And negative values handles negative no dot val or target sum correctly. And also we are handling single node here. If root is a leaf and root dot val is equal to target sum, returns root dot val. So returns an element with just root dot val. And then so I would like to talk about the level order traversal here. So basically a level order traversal of the tree would visit nodes in the order. Let me take that one. So level 1 root node 5, level 2 left and right children of 5, which is 4 and 8, level 3 children of 4, which is 4 and 11, which is 4 and 8, which is 11, 13, and 4. And level 4 is children of 11, which is 11 and 4, because 13 is a leaf node, which is 7, 2, 5, and 1. And yeah, so we have only 4 levels here. And so that's the level order traversal. So we have level order construction here. So let's take a look at the build tree code. Here first we are validating the input. We are checking if the array is null, empty, or starts with null. And if true, it returns null and empty tree. And then we are initializing the root and the queue. And So here we are creating the root node with ARR of 0 is equal to 5, and we are initializing a linked list queue here, and to process nodes level by level and add the root to the queue. And here we are setting the index I is equal to 1, and within the loop we have we continue the loop while the queue has nodes and there are elements left in the array. And here we dequeue a node and assign its children, and we are processing the children for each dequeued node. Left child, check if I is within the bounds, and error of I is not null, and we create a new node for the left child and add it to the queue, and increment I to move to the next array element. And then here for the right child, again we do the similar process for the right child. And yeah, so that's how we build a tree. And yeah, thank you for watching. Let's meet in the next video.